Right, excellent. We're live. So welcome everyone. Welcome to Astronomy on Tap London, launching for the first time from our homes to your home. So the principle of Astronomy on Tap is that astronomers would meet you in a pub and share with you the wonders of the universe. So please get yourself comfy, get snacks, get a drink whilst I explain what will happen in the next more or less hour. So I'm Romain Meyer. I'm a PhD student at UCL, and I will be hosting this session with Cara Circosta. My specialty is about faraway galaxies, and I also very much enjoy outreach and organizing these kind of things. Cara, do you want to say some things about you?
Hi everyone. Yep, my name is Chiara Circosta. I'm a postdoc at UCL. I moved in London last October. I work on galaxy evolution and supermassive black holes, but I also like a lot organizing outreach activities.
Right, excellent. So for tonight, we will have two talks of about 15 minutes, and you will be then able to ask questions, live questions on the chat to the two speakers. So please do so already during the talks. Cara and I will be monitoring the chat, and we will be picking up questions to be asked to the speakers afterwards. So tonight, first, we have Roger Wesson. Hi, Roger. Roger is a researcher at UCL, and he's spent most of his life between Chile and the UK. But in his, in his spare time, he really enjoys visiting any places on Earth, and especially the most remote ones. So I think you've been to what, 100 places, Roger?
Well, it depends a little bit on what you count as a country and what you count as a visit. Let's say it's about between 80 and 90 countries that I've been to so far.
That's quite impressive. So Roger will be talking tonight about the history of the Hubble Space Telescope, which is, I believe, one of the most beloved telescopes by both the public and professional astronomers. Chiara, do you want to introduce our next speaker?
Yeah, so the second speaker is Corentin Cadiou. He's a new researcher, a postdoc at UCL. He joined us in October. He's from France, and yeah, apart from a great researcher, Corentin is also an expert on French cheese. So if you need advice on cheese, you can ask him for sure. Yeah, today he will talk about cosmological simulations, so how to fit the universe in your computer, which is very, very cool. Thanks.
Right, so I see the numbers have been going up a bit and down a bit. So I assume you are all settled and you have something to drink and eat. Call your family, call your friends, just gather around the laptop or a smartphone, because we're just ready to start with Dr. Roger Wesson talking about incompetence plus genius equal Hubble. I think Roger, just you can go with it.
Okay, so let me first of all find the screen. Yep. Okay, can you see my presentation? Okay, good. All right, so welcome all. Glad you can join us for this Astronomy While Trapped event. And I will talk to you about the Hubble Space Telescope and how it's been a tale of a mixture of the most extraordinary incompetence and the most outrageous genius that has resulted in the telescope that we know and love today. I'm giving this talk today because it's very nearly 30 years to the day since it was launched. It was April the 24th, 1990 that it was finally launched. But the history of Hubble actually goes back way further than that, right to the dying days of 1945, when people in Europe and the United States had developed some very capable rocket technology. Let's say no more about that. All you need to know is that after 1945, people thought, what should we do with this awesome, powerful technology? And in 1946, this astronomer, Lyman Spitzer, suggested that a really good thing to do with powerful rockets would be to, in fact, launch a telescope into space. And if you can put a telescope in space, The advantages are immeasurable. You avoid the turbulence of the atmosphere, you avoid city lights, you avoid all of the problems that come with observing from the ground that actually make it really quite difficult. You can see ultraviolet, you can see infrared. You can do much more from space than you could ever do from the ground. And all you have to do that is launch a telescope into space. So that was the plan in 1946. It took a long time to actually begin development, secure the funding, start building the telescope. That began, oh, I should say, it was decided to name it after Edwin Hubble. He had discovered that the universe was expanding and given us great insight into the history of the universe. And the idea was that the space telescope, named after him, the Hubble Space Telescope, would build on his work and tell us what was going to happen to the universe. Edwin Hubble, seen here in full observing mode. Sad to say that at most of the major observatories these days, smoking a pipe while at the telescope is frowned upon. That doesn't usually happen anymore. But the Hubble Space Telescope actually began construction in 1972, very nearly 50 years ago. It was, right from the beginning, it was a technologically ambitious, too ambitious project. It was fraught with delays. The funding kept on being cut. The project kept on overrunning. In fact, in 1974, it was cancelled entirely, but then it was reinstated in 1976. And by 1978, a little over 40 years ago, the telescope assembly was fully constructed, and all that was needed then to finish it off and get it into space was the mirror. And the mirror is the most important part of any telescope. And in the case of Hubble, they decided that this mirror was going to be the best mirror ever made. It was going to be absolutely flawlessly perfect. And to be flawlessly perfect, what they decided it should be is so flat that the largest imperfections on its surface would be no more than 10 nanometers in size. And that is almost incomprehensibly small. The human hair is 10,000 nanometers across. So it's a tiny fraction of the width of a human hair. In fact, your typical virus, sorry to mention a virus, the typical virus is only 50 to 100 nanometers across. So 10 nanometers is unbelievably flat and perfect. And this was going to take a very long time. In fact, it took more than 2 years to grind the mirror to that level of perfection. Here it is at the very start, 1979. You don't really need the year at the top left there to tell that this is the late 1970s. That technician there dates it quite perfectly. And so the mirror was going to be 2.5 meters across, and these imperfections of 10 nanometers, if you scaled that mirror up so that it's the size of the Earth, 12,000 kilometers across, then those imperfections, the largest imperfection would be about 15 centimeters high. So that is just an incredibly stringent requirement. And yes, it took 2 years to polish the mirror. Here it is at the end of the process being inspected. That technician in the middle of there is saying, do you think we missed a bit? His friends around him are saying, no, don't be stupid. I'm sure it'll be fine. So the mirror was finished in 1981. Then they had the launch was scheduled for 1983, but construction kept on slipping. There were further problems and delays. And eventually the launch was, when the telescope was fully built and ready to be launched, it was 1986. Tragedy struck in 1986. The Challenger space shuttle exploded shortly after launch. And for that reason, at that point, all further shuttle missions were cancelled. And the future for Hubble was suddenly uncertain. They did not know if or when it would be safe to launch the space shuttle again, which was needed to put the Hubble Space Telescope into orbit. So that introduced extra delays. It turned out to be another 4 years before the space program was ready to launch the Hubble Space Telescope. April 1990, there was in fact one final aborted launch that was aborted 4 minutes before liftoff for technical problems, but that was luckily just one final small delay. And on April the 24th, 1990, the telescope was launched into space. So that's 45 years of work and effort to get it to that stage. And everyone was hoping that it would be an extraordinary success. So the image I'll show you next is one that is not often shown in discussions about the Hubble Space Telescope, but it's actually the very first image that the Hubble Space Telescope ever took. And here it is. And you can see it's not very spectacular. That was expected. This wasn't going to be the mind-blowing, beautiful images that would surely come later. What this was just an engineering test to check how the optics were functioning. And on the left, you have a ground-based image of a few stars. And on the right, you have what Hubble could see when its shutters were first opened. And you can see it's not that much different. You don't see any more stars. What you see perhaps is that the star at the top center, which looks more or less like a single star from the ground, you can see that it's in fact 2 stars in the Hubble image. But this wasn't going to be a mind-blowing image. What the plan was that the stresses of launch and being in orbit would disrupt the optical path a little bit, and the telescope would need to be adjusted to bring it to a perfect focus. And so the plan was they would take an image, they would check how it was and what needed to be done to perfectly focus the telescope. And soon after that, they thought a couple of weeks of work and checking, they would be in the position to take all of the wonderful images, pass around the large cigars, sit back and enjoy the fruits of their decades of hard work and labor. Well, did that go to plan? It did not. It did not. They found, in fact, that they could not bring the telescope to an optimal focus. No matter how they adjusted it, the star images did not look like points of light. They were supposed to, stars were supposed to look like the small point of light right in the center of this image. But in fact, the best they could do, the best focus they could achieve, still smeared out the light over such a large area that it was basically no better than what anyone had ever done from the ground before. They had spent $1.5 billion and they'd spent 45 years working on this telescope only to find that it wasn't working. It wasn't any better than what was happening on the ground. So how on earth had this happened? What went wrong? Well, there was a lengthy investigation, and it turned out that the company that built the mirror, they had 3 machines to check that the mirror was exactly the right shape to this perfection level of 10 nanometers. And one of the machines told them that they were bang on track. The mirror was perfect. 2 of their other machines hinted that there was a problem. But this company was under pressure, over budget. They needed to get the mirror built. They decided that their one machine that told them the mirror was correct, that was their most high-tech, most expensive, most awesome machine. They thought that had to be right. And the other 2 couldn't possibly be right. Well, it turned out that that machine had one crucial little flaw. There was a dial that needed to be set to calibrate that machine internally. A fleck of paint had got into the machinery and appeared on that dial, very close to the position of a marking that needed to be read off. And a technician mistook the fleck of paint for the marking that he needed to align the instrumentation. And there was a 1.3 millimeter error in where one of the internal parts of this machine was set. And that ended up ruining the mirror. It's made it ultimately too flat. The mirror was not curved enough in the center. It was too shallow by 0.002 of a millimeter. And that's a very tiny amount. If you scale up that mirror to the size of the Earth, that corresponds to being too flat by 10 meters over the size of the Earth. So this is a minuscule difference, but that was enough, given that it needed to be correct to 10 nanometers and it was 2,000 nanometers wrong. Then this was such an enormous difference that it basically ruined the stellar images. And here's a tragedy. There was actually a perfect mirror that had been ground as a backup by a different company. And that mirror never saw starlight. Had this problem been discovered before the launch, it could certainly have been put into the telescope as a replacement for the faulty mirror. But because the problem was not discovered until the telescope was in orbit, that mirror was never used, never seen starlight, remains in a museum to this day. So this was a public relations disaster. What all astronomers thought would be a really spectacular boon that would get the public totally enthused about astronomy forever after was in fact a public relations nightmare. And it was all over the news, all over the press for a very long time. A Newsweek issue here from 1990, NASA's 1.5 billion blunder, bit of a disaster. It got worse. In the 1991 film, Naked Gun 2.5, Lieutenant Frank Drebin goes to a bar where depression and failure is highlighted. In the background at the top right, you see the Hindenburg. In the background at the bottom left, you see the Titanic. And in the background at the bottom right, yes, in the background, in orbit above Earth, it's the Hubble Space Telescope. It was that much of a failure that it was even considered representative of failure to the same extent as the Hindenburg and the Titanic. So what could be done? There were fortunate situations that allowed the scientific community to recover from this epic disaster. The main thing was that Hubble was designed to be repaired in orbit. It was anticipated that the space shuttle could go to Hubble every several years and make repairs as components failed. It could top up the fuel, it could replace the batteries, and it could replace old instruments with new instruments. And so in 1993 was the first Hubble servicing mission. And it turned out they could repair the mirror in a sense, because the mirror was wrong, but it was wrong in the most incredibly accurate, precise way. The shape that it had been ground to incorrectly was extremely precise. So they knew exactly what shape it was, and they knew exactly what shape it should have been. So in fact, all they had to do was make another mirror with exactly the same error, but in the opposite sense. Where the main mirror was too shallow, they made another smaller mirror that was too deep in exactly the same sense. And all they had to do was put that into the optical path of light, and it would fix the problem entirely. So because the machine that ground the mirror was incredibly accurate, just sets the wrong value, the problem could be fixed. And so this was obviously another huge expense. People had argued that the whole thing should just be cancelled. But the servicing mission went ahead, the telescope was repaired, and soon after that, things got dramatically better. Here is on the left, is one of the last images taken before that servicing mission of the deficient optics, the light all smeared out, not much detail. On the right, the same object observed shortly after the servicing mission, and it's a vast improvement. The resolution is fixed, it's back to its nominal specifications. And at this point, they did hand round the giant cigars. They all sat back and appreciated the fruits of their labor, because at this point, the Hubble Space Telescope worked perfectly, and it began to return just the most astonishing results time after time after time. I'll show you some of the most spectacular images that it was able to get. Here is an image, in fact, taken from the ground of a region where stars are forming. And it's one of the big puzzles in astronomy is exactly how do stars form? And we see that they are forming with inside these fingers of dust. This is an object called the Eagle Nebula. Those pillars are called the pillars of creation. And when Hubble looked at that after the servicing mission, it revealed unprecedented detail, incredible fingers and tendrils of gas within which the stars themselves are forming in a way that has never been seen before. And it got even better. Subsequent servicing missions replaced the instruments to even higher specifications. Here is a later image of the same field with a much better camera still 5 years ago. And astronomers will be studying these images for many years for what they reveal about the environments within which stars actually form. Soon after the first servicing mission, there was an incredible opportunity. The planet Jupiter was struck by a comet. This is something that had never been seen before, and Hubble was in the right place at the right time to see what happened to the planet as the fragments of a comet plunged into it. And it took these spectacular images of dark patches where pieces of comet had plunged into the planet's atmosphere, giving us an absolutely unprecedented view of an unprecedented occurrence. Further out, there was a mysterious stellar explosion in 2002. This star with the catchy name V838 Mon exploded and briefly became the brightest star in the galaxy. And Hubble took these series of incredible images of the flash of light illuminating clouds of dust further and further away from the star, allowed us to tell exactly how far away that star was and what was going on and what caused it to explode. It's thought that it was actually two stars coalescing into one and exploding as they did so. Further out still, this is a view of galaxies colliding. This turns out to be a very frequent thing in the universe. Galaxies are always colliding, triggering off massive bursts of star formation, the release of tremendous amounts of energy. And when they merge, they form new, big, in fact, giant elliptical galaxies. We'll hear more about that in the next talk. This is two galaxies of particular interest shown in unprecedented detail as they tear each other apart, throwing out enormous clouds of gas and triggering vast star formation. And still further out, looking into the very distant universe where we see just endless clusters of galaxies. And what we see in this one is a phenomenon called gravitational lensing, where a nearby, relatively nearby cluster of galaxies magnifies and distorts the light from a much more distant cluster of galaxies, which we would otherwise not be able to see. And all of these arcs and lines scattered throughout this image are images of a distant galaxy of clusters, a cluster of galaxies, sorry, being magnified by the foreground. And Hubble detected many of these, and these allow you to characterize exactly how much mass is in the universe, and ultimately to give you a better idea of what its ultimate fate is. Again, there'll be more about this in the next talk. So 2003, another tragedy struck astronomy and the space program. The Space Shuttle Columbia burned up on re-entry after a mission into space. And at this point, as a result of that, all subsequent shuttle missions were cancelled. It had been anticipated that they would keep on servicing Hubble for really as long as they needed to. If they visit it every several years and keep repairing it, it can operate more or less indefinitely. But after 2003, the shuttle program was cancelled, and it was thought that this would mean Hubble would simply fade away, gradually breaking to the point of becoming unusable and would have to be mothballed, essentially. After a lengthy campaign by astronomers, one final servicing mission took place in 2009. It was one more resounding success. It put on new instruments, fixed up all the old ones, and set the telescope fair to operate for many more years yet. Here is one of its more recent spectacular images. This is the famous Horsehead Nebula, shown in detail that you would never be able to capture from the ground. Just extraordinary to see the clouds of gas and dust in space in this level of detail that only Hubble could give us. So what's the future? Currently, it's operating, it's working well. Everybody in astronomy is still desperate to get their hands on Hubble time. The application process comes around once a year, and it's fearsomely competitive. About 90% of applications for time do not get time. You have to be very lucky and very good to get time on the Hubble Space Telescope. And however, there are no more servicing missions. If anything breaks fundamentally, it can no longer be repaired. And if Hubble was left to its own devices, by about 2030, its orbit will decay to the point where it falls down into the upper atmosphere and burns up. This image shows you the Mir space station, to which that happened in the late 1990s. That's what will happen to Hubble. If nothing else is done to it, it will fall to Earth and burn up on the way down and be lost forever. So what's coming next? Well, the reason that it's not too distressing that Hubble will end is that its successor telescope is being built, the James Webb Space Telescope. It will be 7 times larger a mirror. It will be extremely innovative technology. It's got a lot of cutting edge design features. It will be very spectacular if it works. However, it's got to be said, it's followed much the same trajectory as Hubble, with a lot of construction delays, budget overruns. It was even cancelled in 2013. It was then reinstated in 2014. It's currently scheduled for launch in 2021, next year. So fingers crossed. So that is the basic history of how Hubble went from a failure to an epic success. I will finish with one final image of another failure by Hubble. This happened when it was trying to observe a star cluster. Its guiding systems went wrong and it slewed wildly across the sky. And I show you this because I think it's a really awesome picture, even if scientifically useless. Hubble is that good now that even its failures are in their own way quite spectacular and impressive. And that's it. And I'll be very glad to answer any questions that anyone might have.
Well, thank you very much, Roger, for this interesting and inspiring talk. I think we all really like Hubble, and the public really likes Hubble. All the pictures are free, and are usually end up on T-shirts and posters. We will now take questions from the chat. So please feel free to ask any question, and we will read them back to Roger, or Roger can read them actually. Any question from the panel, maybe? So Roger, can you maybe highlight a bit, because people see Hubble and they always say, especially with Elon Musk, the constellation of satellites that's coming up, and it's it's going to block the light, and it's going to add more satellite trays to the images we have from ground-based telescope. Can you maybe highlight what's the pros and cons, and just not in terms of billions of pounds, but why we are why don't we have hundreds of Hubble in space?
Well, the main reason would be the budget. I mean, at the time of its failure, when it was considered a failure in 1990, you saw that Newsweek headline, $1.5 billion. The budget over time, the total amount of money spent on Hubble is like $10 billion roughly over the whole lifetime since it was initiated. And so that's a pretty huge amount of money. I mean, it's very small in terms of what nations spend on many other things, but in terms of science, that's an enormous investment. JWST is going to be by a factor of several much more expensive, because the Hubble mirror 2.4 meters across. James Webb will have a mirror 6.5 meters across, and building mirrors that big on the ground is quite a challenge. But building that and putting it in space and the engineering required is just phenomenally expensive. So that's the limiting factor. The advantage of space, I mean, also since Hubble was launched, technologies have been developed on the ground that can help. They can overcome some of the disadvantages of being on the ground. You have this problem that the atmosphere is turbulent. Light that has traveled for billions of years across the universe gets almost to the telescope, and in the last minuscule fraction of a second as it crosses the atmosphere, it's smeared out and distorted and ruined. But with very clever technology, you can actually distort your mirror on the ground in real time to compensate for the distortion of the atmosphere. That's not the only reason to go to space. You still have the problem of light pollution. You still have the problem that the atmosphere itself glows at night, and that's not something that you experience in space, obviously. So, but yeah, the advantages of space are perhaps a little less. I mean, it's much cheaper to do almost as good a job from the ground as you could do from space. So yeah, the sheer expense of it is why there's still only one Hubble, and why there will only be one JWST.
So JWST in comparison is not repairable. So what's next after James Webb?
Well, good question. I'm not sure if anyone's planning beyond that yet. I think the challenges of JWST are already enormous, and we right now, a lot of us in astronomy, are waiting with extreme anticipation for this telescope to actually be launched. And it should have been launched. I mean, it was a very definitely confirmed schedule that it should have been launched in 2018. And they basically, the information was that nothing could stop it. It was well on track. Everything was in place, and then it wasn't. And launch has been postponed just many times. And in fact, if you can plot a graph for JWST of the expected launch date as a progress with time, and the expected launch date keeps on moving further and further away, but on the current track we'll actually reach launch in about 2026. That's when the time that it's anticipated to be launched should meet the actual time, and at that point, once JWST is in orbit and working perfectly, then I guess people will start thinking about what comes afterwards.
Yeah, this has become a recurring joke in astronomy. I mean, when I started 3 years ago, I was promised James Webb would be, up and running by the end of the thesis. Here I am, no James Webb. Right. Maybe one final question before we switch to numerical simulation with Corentin. So you've used James Webb, Hubble, Roger. So what's your favorite object observation you've made with it?
Well, my favorite Hubble images, I don't know if I can actually show you. Let me see if I can just find the image. Right.
So in the meantime, in the chat, please ask questions if you want.
Do you see an image?
Yes.
Excellent. There is my favorite Hubble image. It's a dying star throwing off clouds of gas. I've studied these images. I published a paper on them. It was one of my very first published papers. So I always have a soft spot in my heart for this image and this object that's known as the Cat's Eye Nebula. And Hubble showed that these types of objects, these stars throwing off their outer layers into space, were far more complex than they ever looked from the ground. From the ground, they always look just kind of spherical, kind of simple, and people thought they understood them. And then Hubble returned us images like this and revealed endless complexity, which we're still trying to unravel.
Excellent. Thank you very much. If you can stop sharing your screen, perhaps. Right, great. So we'll now move on to Corentin, who will talk us about numerical simulation, how you can simulate an entire universe inside your laptop, basically.
Can you see my screen?
Corentin, if I can just ask a question to Roger.
Yeah, sure.
So we have a question from Laura. Are they still imaging V83.8 Mons expansion? I might be mispronouncing this. If you have access to the chat, Roger.
I can't see the chat, sorry, but V838 Mons expansion. I actually do not know when the last image was taken of that. I know that it was monitored because it exploded in 2002 and they were imaging it for more than a decade to show that expansion. I'm not sure if they are still, if they have imaged that again recently. I can check that, I'll look that up. I can answer that a little bit later on.
Okay, great, thank you. We'll come back to this after the second talk. Corentin, here you go.
Yep, okay, great. So hi everybody, thanks for being there. So my name is Corentin Cadiou, pronounced in French, and if you pronounce it in English, it's a bit unfortunate because it sounds like quarantine. And today I want to talk about how to actually fit the universe in your computer, well, either in your laptop, but usually when you're doing science, you actually do it on much bigger computers. I will also discuss the question about whether it's actually useful to do it and whether we actually do it, and how we actually do it. And just to give you some kind of trivia before the talk, I'll just let you a couple of seconds look at the picture in the background and wonder whether it's an image from a numerical simulation or from, for example, the Hubble Space Telescope. So do you think the image in the background is a real one or is a simulated one? And you'll get the answer during the presentation, so stay tuned. All right, so the first question is whether do we actually need numerical simulations, because, well, believe me, it's quite a pain to write them and to run them. So do we actually care? Why do we need it? And by explaining that, I'll hopefully give you some ideas about how we actually do it and what they actually do represent. So essentially, as Roger showed in his talk just before, we can make very nice images of galaxies or of the universe as a whole. But well, one of the issues is that we'll never see a galaxy evolving. And by that, I mean that let's imagine that you're a dinosaur and you take a picture of a galaxy. Well, if you do that, for example, let's take a picture of the Triangulum galaxy, which is a galaxy just right next to us. Imagine that a Stegosaurus 65 million years ago took a picture of the Triangulum galaxy. And then today with, for example, the Hubble Space Telescope, we can make a picture of the galaxy today. So, well, you can sort of see here that there are some differences. Obviously, I cheated here. I made the pictures myself because we don't have records from dinosaurs. But essentially, the bottom line is they're the same picture. So what I want to say about that is that in 65 million years, the Triangulum galaxy had only the time to make 1/4 of rotation. What this means is that during the lifespan of a human, we are absolutely, it's absolutely impossible to see one galaxy even just move on a picture. And even if we had record from the first humans a couple of hundreds of thousand years ago, they would also have they would see exactly the same sky as we do today. So since we can't see the universe evolving well, how do we know it's actually evolving? And how do we understand how the different pieces of the universe interact one with each other, where they come from, where they're going to? Well, essentially, you can think about it as being a gigantic puzzle with, well, not thousands of pieces, but billions of pieces. So for example, here it's an image from the Hubble Space Telescope that Roger presented before. And as scientists, what we want to do is understand how each of the pixels here, each of them are one single galaxies, how they actually appeared, where they come from, how they're going to evolve as a function of time. And well, the universe is not very nice to us. It gave us all the different pieces, but it doesn't tell us, well, it doesn't tell us where they came from and also how they're going to evolve. So you can imagine that you take all the pieces together and you try to reconstruct the puzzle of the universe. But of course, because there are billions of pieces, it's really too hard to do. So imagine that I'm given this task, I just wouldn't do it. And this is not what I do. Instead, well, you can rely on, well, on computers, because they're really good at crunching numbers, and billions of galaxies, they don't really care. They can do that in a couple of seconds. So essentially, you can imagine programming a computer to try to reconstruct the universe and take all the different pieces and make something that makes sense out of it. So do we even need numerical simulations? Yes, we do. And let me illustrate that point with a simple example. So essentially what we want to do, we want to see the universe move. We want to see galaxies rotate. We want to see galaxies merge. We want to see galaxies do stuff and not just be still on a very nice picture from the Hubble Space Telescope. So what we want to do is create a universe in a computer so that we can understand the real universe that we'll never see moving through telescopes. And I'll just going to replay you the background animation. Essentially, it's a bit as if you had the triangle galaxy and you wanted to see it rotate. So here, of course, I'm cheating because we can't see it rotating. It's an animation that I made myself, but I'm going to present some simulations later that actually show galaxies evolving in a simulated universe. All right, so that's a plan. How do we actually do it? So I just said that it's useful, but I didn't say how we can actually do it. Well, when you think about a universe, essentially the universe is everything that exists at all times. So if you want to simulate the universe, the first thing you have to do is you need to create a box with space and time. And then once you have space and time, well, you can start including the known physics. For example, you can include gravitation, chemistry, so how different elements interact one with another, stars, so how do they form, how do they eventually explode, how do they emit lights that we observe through telescopes, but also black holes, how they accrete matter, etc., and dark matter. And a lot of different processes that I'm not going to list here. If you want to make an analogy, you can imagine that the box for space and time is a bit like a bowl that you would have in your kitchen. And then the known physics is just a bunch of recipes that tell you how to transform flour and eggs into pasta, for example. So right now I've got the box, I've got my bowl, and I've got the recipe, which is my known physics, which tells you how to transform stuff. But then I need some stuff. And my stuff is actually the initial conditions. So if I go back to this analogy in the kitchen, you can imagine that if you want to make a soup, well, you need some potatoes, you need some carrots, and then you put the potatoes and the carrots, for example, in your pot, and you start cooking. Well, the potatoes and the carrot are your initial conditions, and then you want to see how the soup emerge out of your pot. And this is really what I want to do with the universe. I set some initial conditions, some rules to tell my computer how things are supposed to evolve, and then I let it evolve and I see what happens. So the next step is to let things evolve. So if I do that, if I put some initial conditions and I press the forward in time button, I get the image that is on the bottom right, which is one of the simulations that I run myself on very, very large scale. So here, each little dot is actually one single galaxy. I'll come back to this point later. And so now you've got one realization of one fake universe, and you can start doing things. For example, well, you can, oh yeah, sorry, I forgot to mention that running the simulation actually took months. So it's not very quick, but it's much faster than the universe, which took 14 billion years to create us. So once you have your simulation, you have the whole universe at all times, at all positions. So you can start doing things, for example, doing science. And one thing you can do, you can imagine taking one small part of your simulation and make a fake image. So I answered a question that I was at the very beginning of my talk. This is a fake image that was created out of one of my simulations. And you can, for example, compare it to observations made through through telescope like the HST. And this is really interesting because if you find some discrepancy, it tells you that your recipe, either your recipe is wrong or your initial conditions are wrong. So you can do this back and forth loop to improve your knowledge about the universe, in the same time understand how galaxies form. And you can also make some predictions. So you can say to your best friend that is doing observation, hey, you should look at this particular spot in the sky and you should see that kind of things. And either they do or they don't. And in both cases, well, you learn something new. Okay, so now we know how to do simulations. We know it's useful. Well, let's look at what comes out of the of one of the simulations. So let's just do a simple example to start with. Let's look at the merger of the Milky Way and the Andromeda Galaxy, which is our neighbor. So the Andromeda Galaxy is here, the Milky Way is here, and this little thing is actually the triangle of the galaxy. So if you put that in a numerical simulation, this is what happens. Essentially, well, due to the action of gravity, the Andromeda Galaxy is pulled towards the Milky Way, and the Milky Way is pulled towards the Andromeda Galaxy. And if you wait long enough, a couple of billion years, well, essentially they're going to merge. And this is quite interesting because, well, first you know it's going to merge. You also know how two of these galaxies, well, what is the outcome of the merger of the two galaxies. And you can ask questions as, for example, what is going to happen to the solar system? Is it going to be ejected from the galaxy, etc.? But really here, I've only described two galaxies merging. Well, they're interesting because they're our own, but it's really only two galaxies. And when you look at the sky, you see not two, but billions and billions of galaxies. So imagine that you don't want to study just two galaxies, but really all the galaxies in the universe at the same time. Well, in order to do that, what are the initial conditions you should set? Because if you already put the galaxies, you don't understand how they form in the first place. Well, for that, let's follow the Big Bang Theory, which tells us that our whole universe was in a hot, dense state and homogeneous. I forgot about this one. Then nearly 14 billion years ago, expansion started, and all started with the Big Bang. So essentially, well, it gives us a recipe. Well, it gives us the initial conditions. Let's set a hot, dense state as well as homogeneous, and then play forward in time. That's pretty easy. And if you do that, well, you get that kind of picture. It's buffering. It's still buffering. Okay. So here, what you can see is bright spots are the dark matter density, and the brightest one are where you have the most dark matter. And you see that as time goes on, you have more and more matter going there. And you can also look at the gas instead of the dark matter. And what you see is some very striking feature, which is that the gas seems to align along filamentary structures. So here, once again, each little dot is one single galaxy. So the gas follows this filamentary structure and then flows at the intersection of the filaments where some massive galaxies are going to form. And because I've got like pores, I can also reveal the galaxies in my simulation, and this is what you see. So here it's one numerical simulation, and you see that I do not have just two galaxies as in the Andromeda and Milky Way case before, but instead I have hundreds of thousands of galaxies. So I can study how this this massive number of galaxies interact one with another, how they are in space, etc. And really here, galaxies do not appear anywhere in the universe, but they instead form a cosmic web. So they form along filamentary structure. So that's one thing we see in simulations, but also in observations nowadays. Right. And so so here I was looking at the population of galaxies on very large scales, and it's not really yet answering the question about how, for example, spiral galaxy forms like our own. So for this, you can imagine taking the same simulation as before, but this time you zoom in extremely, and you look at very small scales. So here I'm showing the density of matter in the universe as a function of time. On the bottom left, you have the density on much larger scales. And on the bottom right here, where I'm showing, you have actually an image of the galaxy that would form here. So on the bottom right is some kind of images that you would get out of a telescope. And I'm playing forward in time really quickly. And really one thing that is amazing with simulations is the fact that you have godlike powers on the simulation, which means that at any time I can ask the simulation just to stop, and I can rotate the view and see what are the structures in 3D, where does the gas come from, and also what other quantities are, for example, the temperature or the velocity. So, well, let's stop the simulation and let's rotate the view. So first you see that, well, it's not only, well, you can see some 3D structure, very complex ones, which are painful to analyze and understand, but that's my job. And you can look at other quantities, for example, here, pollution from the galaxy, how much, so yellow is a lot of pollution and green is much less polluted. If you have question about it, just ask me. You can look at the velocity of the gas, where bright spots are high velocities. You can also see whether the gas is infalling towards the galaxy in blue or going outward in orangish. And of course, because I've got like powers, I can also say, okay, that's enough. Let's just make a picture that I would get out of a telescope, and this is what I would get. Ish. All right. Okay, so am I with time? Yeah. And then of course I can resume and keep on going until I've run 14 billion years. So far I've only done halfway through the history of the universe. We're approximately at 7 billion years after the Big Bang. So that's at the history of the universe. All right. And just to give you some idea of the technical challenge that this simulation represents, here I'm taking one of my simulations and I'm zooming out from the small scale, which is where one of my single galaxies is forming, which you can see here at the center of the image. And I'm going outward. And if I want to give you some analogy, the resolution of this simulation is good enough that if you had exactly the same resolution and you took a picture of London, you would be able to see individual 1 pound coins on the picture if you were to zoom enough. And that's the kind of resolution that we are talking about. And you integrate that for 14 billion years, so you've got thousands and thousands of different images as a function of time. All right. So if I want to sum up the question that I asked at the beginning, well, we can fit the universe in a computer, and it's actually very useful because it gives us insights about the evolution of the actual universe. We don't have access to the evolution of the actual universe. So reproducing a fake one in a simulation gives you access to this evolution. It gives you some a better understanding of the physics, how they play one with another, and makes very nice images. That's really cool. And well, I guess that's all for today. Don't hesitate to ask questions either on YouTube or just on YouTube, actually. Thank you.
Excellent. Thank you very much, Corentin. Maybe if you, well, we can keep on that screen for now.
Yeah.
So we have first question for you, Corentin.
Yeah.
So you've been talking about you've been showing your own simulations, your own work, which is quite amazing. So James Moore is asking, what has been the one thing that has surprised you? So you probably had an idea about why you should do that simulation. What has surprised you, and are they variable? What's the tricky thing? The most difficult thing to determine when you run these simulations?
Yeah. So I guess one of the things that so when you study physics, usually be it in high school or at university level or at master's degree or even at the beginning of a PhD, well, most of the things that you see are actually pretty simple. I mean, the understanding of the physics is complicated, but then the models are very simple. I don't know, for example, when we study atoms, we usually assume that they are spherical and things like that. what really struck me when I was running simulation was the fact that when it comes to galaxy formation, absolutely nothing is simple. There is no such thing as a simple formation model of galaxies. If we just go back to this thing here, well, you obviously see that it's a gigantic mess. And here I'm only showing the gas, but then if you look at other things like the dark matter or the temperature, it's even worse. So really what struck me was the fact that it was the end of the simple days in terms of physics, and it was the beginning of something quite interesting. But hopefully you can tame and understand all this complexity using numerical simulations, because you can stop and inspect all the different aspects, make all the pictures that you want to actually understand how these complex physics play one with another.
Okay, thank you. So we have other questions, maybe?
Just for precision, the simulation that I'm showing here is not due to me, but it's due to a team in Germany. But the other plots are actually made from simulation that I run myself or with collaborators.
Great. Chiara?
Yeah, there is another question by Laura. She's asking whether the whole simulation was run at the same resolution, or is it adaptive mesh refinement, or is everything zoom in after? And how big are the files for this?
Yeah, I didn't mute myself. So for the people who don't really know about it, adaptive mesh refinement is a way of somehow cheating. So here on this slide, I was showing that we have an exquisite definition, like the definition of the simulation is really, really high. We can't afford to have the same resolution everywhere, because it would just require much more computation power that is available in the entire world. So instead, we use something that is called adaptive mesh refinement, which is one strategy where we only put resolution where there are things that are of interest to us. For example, here I'm interested in this galaxy, so I only put resolution around this galaxy, and you can actually see the pixels. In the regions where I don't have the galaxy, you see very big pixels. This is because I just asked my computer, okay, I don't care about what is happening far away from my galaxy, so just don't put any, well, don't get yourself into any trouble, and just don't put any resolution there. But there are also other techniques that I didn't mention. For those interested, you can look up SPH or ask me some questions on Twitter if you want. But what was it? The entire question, or?
Yeah, and then how big are the files for this?
Oh yeah. Okay, so for the simulation that I'm showing here, I have each output is 100 gigabytes, and I have 200 of them. So in total, that's 20 terabytes of data, which is well, you can imagine how painful it is to analyze. For reference, I can store 2 outputs of my simulation on my computer. So at the beginning, I was saying, how can you fit the universe within your computer? Well, you can't really. You can fit the universe. You can fit 2 outputs of your simulations, and then, well, you don't have storage anymore. Just to give you some numbers, it takes 1 hour to read all the data from the simulation once. Which means that whenever you want to read something, you have to wait 2 hours for it to actually physically read. So yeah, that's quite annoying.
So it's great. It leads you to another question. So you said you were cheating. I mean, it's not really your laptop. So someone is asking, are you running your simulation on a supercomputer, and how long did it take?
Yeah. So just I anticipated these questions. I tried, but unfortunately I didn't have time to finish it. You can actually create a numerical simulation that runs within your browser. If you want, I'll probably tweet it sometimes later. And the best performance I had was I could run live 10 by 10 by 10, so 1,000 particles at the same time. And this simulation here has 1 billion particles, so 1 million times more. So of course I couldn't run it on my computer. I did run it on a cluster, so on 500 computers at the same time. So yeah. So yeah, most of the simulations are actually run on supercomputers. Well, the ones that I did myself is fairly small compared to, for example, this simulation here, which ran for I don't know how many months on I don't know how many cores, but that's really, really massive.
And then we have another question by Francisca asking what kind of scales you can resolve in your large-scale structure simulations, and then if there is any physics that you would like to include in the future.
Yeah. So if I go back to, let's take an image that is simple enough. Yeah, for example, in this simulation that I'm showing here, the size of the box in total is about 100 million light years. So it's much smaller than the universe, which is I think it's 45 billion light years across. But there's not really any limits on. There's no upper limits on how big the box you want to do. But of course, if you increase the size of the box, you are going to decrease the smallest resolution that you have. So if you want to see the universe really on the most largest scale, well, you're probably going to miss what happens in terms of the formation of galaxies, which is what I'm interested in. But you can keep, well, you can imagine that the ratio between the small scale and the larger scales is about 1 million. So that's part of the resolution. And among the things that I want to include in terms of physics in the future, well, I'm still quite satisfied about the set of physics that I'm using right now, because I still can't understand how galaxies form. So I think I'll stick to the good old physics for now. But maybe one thing that I would like to include is the effect of, for example, neutrinos, but I'm getting very much technical. But I mean, you can add all sorts of physics and see how it impacts the formation of galaxies or the formation of the universe as a whole. That's one thing you can do through numerical simulations.
Right. So now that you have all your wonderful blocks in your simulation, the question is, if you start modeling the current universe now, so you've evolved it from the Big Bang to now, and then you let it run for, I don't know, another 14 billion years, what does it predict? What does the future look like?
It's quite boring. No, so you can actually do it. I mean, who's asking the question? Is it on YouTube or?
It's on YouTube, yes. Okay. So I've just repeated the question.
Yeah, sure. Okay. So the thing is that I didn't mention it in this talk, but the universe is expanding. I mean, I did mention it through the Big Bang theory. So the universe is expanding, and what it tells you is that well, the more you wait, the larger the more space you have. And currently, so right now, as of today, the expansion is being accelerated exponentially, which means that things are getting stripped away one from another at a pace that is growing exponentially. So what it means is that in the future, all galaxies are going to end up being isolated one from another, which means that, for example, scenarios where you have, let me try to pull it. Yeah, scenarios like the merger of the Andromeda galaxy and the Milky Way are going to become less and less probable. And in a very, well, in a tens of or hundreds of billion years, it's actually going to be impossible to have two galaxies merging, which means that each galaxy is going to be its own island universe, probably, and eventually at some point you won't even be able to see any other galaxies than the one you're standing in, which will be extremely complicated for future astronomers to try to understand the universe, because they won't be able to see it. But yeah, essentially, so what I'm describing right now is the theory of the Big Rip, which is the fact that if you wait long enough, things are going to accelerate so fast away one from another that any interaction is going to become impossible, and it's going to become impossible to see anything, well, anything far, essentially.
Right. Maybe if you stop sharing your screen.
Yeah.
We have one final question to consider, I think, amongst maybe more for Roger. What about an observatory on the moon?
That would be pretty amazing. There would be a lot of, there would be even more things that you could do from the moon that you couldn't do from Earth. For example, one of the big problems on the Earth is if you're actually not looking at optical light, but radio light, it's an ever increasing problem. There's interference from everywhere. It's very, very, very difficult to find somewhere that does not have radio interference. One of the best radio observatories in the world right now is in Chile at 5,000 meters above sea level. It's a very remote, very inhospitable environment. I've been there. The atmosphere was so thin that when I came back down, I could not remember what I had seen and what I had done up there. I was so oxygen deprived. If it was possible to build a radio observatory on the moon, on the far side of the moon, then you could, for example, you could use a crater on the moon as a natural radio telescope and put an instrument at the focus of that crater, essentially. However, I mean, it would be amazing because then you would have no interference. You would have an enormous possibility to build a very large telescope. But the cost of that is beyond anything humans can currently comprehend. I mean, the challenge of putting a telescope in orbit, basically 300 miles above the Earth, is enormous, and it's very difficult, and it's only been done a handful of times. The challenge of building something on the moon is just vastly greater. So I don't think it will happen for a very long time, but it would be extraordinary if it's. I mean, if one day it is possible, then whatever telescope they build on the moon will be the best one that has ever been built.
Just if I add a comment on that, there are actually some meetings happening in the astronomy society, among astronomers to actually do it. But of course, without any timeline. But there are some people that are brainstorming about how to actually do it, and where you would go, and how much it would cost, etc. But it's not going to happen anytime soon. But that's interesting.
So yes, I think we can thank again our two speakers. Thanks for being guinea pigs for this first Astronomy on Tap London and first virtual Astronomy on Tap London. I think it's been great. We will have another event probably in 2 weeks. So subscribe to the channel, follow us on Twitter. I've added links in the chat. And if you don't have enough of Astronomy on Tap, if you want more astronomy streamed down to your couch, Astronomy on Tap exists all around the world, and many satellites are doing events. And for example, tomorrow there is a 7-hour marathon of astronomy talks that is streamed by, that is hosted by the Astronomy headquarters in the US, and it will progress throughout the day from the US to Europe. And so you can tune and try to follow this. I've put the link again in chat. On that note, I think we will say goodbye and see you in 2 weeks for even more astronomy. Stay safe and keep looking at the skies. Thanks.